No?
Hello.
No.
Hello, Augusto.
So we're just missing Flavio, Marcos, Patrick, and Paulo. Rodrigo and Giovanni. Oh, Giovanni's here. So Rodrigo, Paulo, Patrick, Marcos, Flavio. Let's wait 3 more minutes and then we start. Oh, Patrick. Okay, let's start then. I will start sharing my screen whenever the other participants enter. I will have to leave the presentation back.
Hi, Professor. May I ask a question?
Of course. Of course.
We will not use the Moodle.
Yes, we will use Moodle, but I don't have a number yet.
Yeah. Oh, perfect.
So probably next week, maybe it will take longer. I'm sorry about this. It probably makes it much easier for you guys. Maybe some of the students don't have the link. So that's, and yeah, but we're recording the lectures. Natalia is recording the lectures, and then I'll share with you if you want to hear something that you missed. Okay, so Rodrigo's here. We are just missing Paulo, Marcos, and Flavio. We can start. So today the lecture is about hydropower energy storage, but we will start from where we stopped last week, which was the introduction to energy storage. And we stopped at heating and cooling sectors. So another aspect of energy storage, which will become relevant in the future, is because you're not going to burn gas or coal or biomass for heating. The biomass you continue burning because it's sustainable, but this coal energy and gas, which is used nowadays, will have to be replaced by other solutions. And of course, hydrogen will play a large role because it uses the same infrastructure as methane. Of course, it needs to be upgraded because the hydrogen will cause damage the infrastructure, but changing the infrastructure is not as expensive as creating a whole new infrastructure. And of course, there are a lot of different other options for storing and storing heat, thermal energy. There are some which are already mature and used nowadays, particularly in countries in the US or Denmark, in the northern hemisphere, where you have very cold winters and potentially hot summers. One solution is aquifer thermal energy storage. You have one section of an aquifer which is not connected to another section. And the idea is that once in the summer you need cooling, one of the aquifers store cold water, and then this cold water is pumped, and then the cold water is used to cool down a building or a house. And then this hot water that comes out of cooling down the building is stored in a hot reservoir. In the winter, the heat stored from the summer in this aquifer is then used to cool down, to heat up the building, and the cold water produced from cooling winter temperatures is then stored in this other reservoir, and then this cycle starts again. So it's a very energy efficient solution. You just store energy from the summer to the winter. I have to accept somebody here. Hello, Marcus. There is also ice storage. Ice storage is used in Japan for a reasonable amount of time today. There is more new technologies being developed. This is one example. You have a tank and you use
Good afternoon.
ice. Good afternoon, Marcus. Use ice by the problem with ice is that it has a very high heat insulation capacity. So in order to freeze the whole tank with ice, you need coils, you need fine solutions, and this is one of the solutions for ice storage. Another one, which is also mature and used nowadays, particularly in Denmark, it's a very Denmark technology, is basically to dig a hole, a pit. You insulate the pit and insulate thermally and not to leak water. And then you fill up this pit with water. In the summer, when the temperature is warmer outside, they run the water through heat exchangers and they heat up the water. But then in the winter, when the temperature reduces significantly, the water here is warm, and then they use to increase the efficiency of district heating plants. These are probably not going to be a viable solution in Brazil because first, we don't have district heating. Second, the temperature variations are not so high. You need very cold, hot summers and very cold winters in order to be a viable solution. And continuing this introduction to energy storage, we have different alternatives for energy storage. One alternative is to diversify the sources of energy. For example, when you have a very hot day and it's very sunny, it's not raining, so you reduce the amount of hydropower during that day. And usually when it's very hot, the wind is lower, and then you generate a lot of solar power. When it's raining, when you have a month that rains a lot, you generate more hydropower. And when it's not windy, you can use other solutions. For example, some of the biomass they stored, or geothermal, or even coal, nuclear, coal and natural gas with carbon capture storage and nuclear power. So the idea is diversify as much as possible in order to reduce your reliance on energy storage. So this is the prediction for the US. one of the predictions for the US electricity generation until 2050 produced by the National Renewable Energy Laboratory. And another aspect for estimating how much storage you need for your grid, for your energy solution, it will vary with the amount of intermittent variable energy sources, so wind and solar and tidal power. So if you have only 20% of variable energy sources, you would only need something like 5% of install capacity, battery install capacity. You only need 27 gigawatts of battery if you have 5% of variable energy percentage. If this variable energy percentage increases to 90%, then you will require a lot more backup energy storage capacity. So that's the storage that you need, capacity, in order to meet the variable energy storage. Here it doesn't mention the actual storage of energy, because it just mentioned how much capacity. So I'm going to go through this node example. This is a very important aspect of energy storage. One thing is you can store energy, and the other thing is that you can generate energy with the energy that you stored. Two different things. The second one is to increase the number of variable energy storage. So you double the amount of energy that you produce, and you assume that something like 30% of the energy that you produce is going to be curtailed. So you're basically not going to use, because it's cheaper to ditch, to throw away some of the energy that you generate instead of storing it. So this is another option to increase generation and assume that some of it will be wasted. And the third one, which is also very interesting, is to reduce the demand of electricity when you don't have so much supply, which is called demand side management. There are several alternatives. These thermal energy storage solutions are usually also named demand side management. So demand side management and energy storage, they go together in some cases. Some cases they don't, but is also an interesting alternative. Please let me know if you guys have any questions, any opinion or points of view. Feel free to stop whenever you feel like. So this is also a very important slide, which is the energy storage methodology. Literally, what is energy storage? So energy storage, basically, you want to store a commodity, usually electricity, could be energy, could be heat, could be temperature. And this commodity, for example, electricity, has to go into a charger to charge the storage container. And then in order to take out the energy, you need a discharger. So it's not only, you don't only pay for the storage container. You need to transform this energy, this electricity, this commodity into another type of commodity to be able to store and then discharge. The only solution which you don't have to do this is ultracapacitors, which the storage container is itself the energy storage facility. But ultracapacitor, you still need to turn AC current to DC current. So you still have this AC DC current technology that you need to pay, and you have losses, something like 0.5%. And then you have to turn it back from DC to AC. So you have to, that's $1 million. Flavio. Hello, Flavio. So this charger, the unit is in gigawatt, megawatts is in capacity, is the amount of energy that you can add to the storage to a certain time. So if you put a lot of money into this, you can increase the storage very quickly. If you add a lot of money into the discharger, you can discharge the storage, the energy that you stored very quickly. And then you can invest a lot of money in the storage container, which will increase the amount of time that you can store energy, the amount of energy that you can store. So most of the cases you have to invest in charger, discharger, and the energy container. So it's three different aspects. Sometimes the charger is the same as the discharger, the same technology. Sometimes it's not. And sometimes they come as a unit. Everything comes together. Depends on the technology. So charger, for example, are the pump in a hydropower plant. It's a river in a hydropower reservoir. The charger is just the river. You don't need to pay for it, but of course, it's a limited resource. You can only use in certain locations if it's viable to build a hydropower plant. Electrolysis for hydrogen. So you need to, if you want to produce hydrogen, you have electricity, water coming in. You have electrolysis, you produce hydrogen, you store the hydrogen, and then the discharger will be the fuel cell for example. There are fuel cells which are reversible, so they function as a charger and discharger. It's more sophisticated, more expensive. It's still under development. It's not already a mature technology. Other examples, the battery, the charger, and the discharger is the anode, cathode, and the membrane. You need the three to charge, and you need the three to discharge. They're also the charger and discharger. And the battery is the amount of chemicals which are in the battery, which can increase the volume, reduce the volume, depending on the design of the battery that you want to use. The storage container for a hydropower plant or a pump storage power plant is a reservoir, water reservoir. It's water at a higher altitude, so you store water with potential energy. A fuel tank for hydrogen. It could be liquefied hydrogen, it could be compressed hydrogen, it could be a balloon of hydrogen. Chemical components, which is a battery. So nickel, lithium, different types of battery. Thermal tank, it's a tank where you store maybe ice or steam, and you can store thermal energy. So this is the container. The bigger the container, the more energy you can store for a long time. The charge and discharger is how fast you can charge or how fast you can discharge. The commodities for pump storage is electricity, for hydropower is water. Electricity is also for batteries and hydrogen. Heat for thermal energy storage, cold for ice storage. And then you have this intermediate storage commodity, which is for hydropower is water. Now for pump storage is water. For hydropower, you don't need the intermediate storage is water. Water comes out, water comes in, water comes out. But in other cases, you put electricity in a pump storage plant. You pump the water, you store the water, and then you pass the water through a turbine, which produces electricity again. So you need this intermediate, which is water. For chemical compounds, for battery, you have chemical compounds, which you have a membrane, and the membrane, the ions flow through the membrane. So you put electricity in, and then the ions from the battery flow from one side to the other. And for heat, for example, it's steam. You're not going to use steam to heat up your house. You use a colder fluid where you store the energy with steam. You don't use ice to cool your house. You use the water that passes through the ice in order to cool down and then cool down. They are the storage commodity, so the intermediate from the commodity that you put in and the commodity that you put out. Of course, each type of storage has a different arrangement, but this is kind of the methodology that can be replicated for all of them. You have energy losses. For example, if you pump, you have something like 10% energy losses, 5%. When you generate, you also have 10% in a turbine for a pump storage facility. You have losses when you charge, when you discharge, and you have losses in the reservoir. For example, you have evaporation. Your reservoir evaporates, it leaks. You have some leakage in your reservoir, which you have to consider. And then the efficiency, the overall efficiency is multiplying the efficiency of both of the three aspects in order to have the final efficiency of the system. The storage usually have a maximum capacity, a minimum capacity, a minimum operation capacity, a maximum operation capacity, and then you have the stored level where you are. And that's it. So different energy storage technologies. So this is the application. I talked a little bit about the application, the need for storage, but this graph gives a better idea. For example, in the duration of the storage that you need seasonal storage. Here's seasonal storage is usually high capacity. You're not going to build a small prototype that stores seasonally because it's expensive to store energy seasonally, so it has to be high capacity. Storing for interseasons, for a week, for a month, also very high. It doesn't make sense to make a small solution that stores energy seasonally. And then when it goes down, it starts to spread more. For example, if you're storing energy for a day, you also would like a higher capacity, but also maybe 1 megawatt for a battery. This is transmission and distribution. Is postergar. Transmission and distribution means that you can store energy daily in order to reduce the costs of transmission distribution lines, as I explained in the last lecture. You have several other ones. It's written in Portuguese, so I might as well read in Portuguese. Segmento de carga, controlar a carga, a potência, a voltagem da sua linha. Esse daqui é o arranque, seria para você iniciar a sua usina. Regulação de frequência, regulação de tensão, armazenamento eólico e fotovoltaico, variações pequenas de isolado. Esses aqui são para sistemas isolados para você garantir o suprimento de energia. Now the technology. So most of the publications around the world assume that seasonal storage is hydrogen. And for pump storage, they assume a day. This one assumes a week. But also there are several pump storage technologies that store energy for a year, for 2 years, seasonally, multi-year, pluriannual storage. Compressed air is also a possible solution. It's not well established, but it stores energy for 1 day, for a week. Batteries can store energy for minutes to days. You have this flying wheel, which is a mechanical energy storage type, which I'm going to talk more in detail. It stores for short amounts of time, mainly to resolve issues with frequency and tension. And you all have supercapacitors for electricity for seconds and milliseconds, which are usually used in computer devices, electric devices, not grid application. Yet, maybe in the future with graphene. So this is the share of electricity energy storage technologies around the world. This is for 2019. Hydropower takes 92.6% of the world capacity. Then you have 5.2% of batteries already. It is increasing very rapidly, this electrical battery energy storage. You have very few compressed air, very few molten salt, mainly for thermal energy storage or working in combination with solar power, concentrated solar power, the one that you heat up steam to generate energy with solar power. Flying wheels also small capacity. But this value for batteries is expected to increase rapidly in the future. But note that this is gigawatts. So this is the charge-discharge capacity. Charge-discharge capacity. When we talk about gigawatt hour, so actually the energy that you store, hydropower pump storage goes to 98% because you have reservoirs that store energy for 3 years. And in order to compare pump storage reservoir that store energy for 3 years, you would need the equivalent number of batteries, which usually store energy for 4 hours, 6 hours, times 3 years. So it would be something like 3,000 times more energy that they store, just because it's easy to pump water. It's cheap to store energy with water. But it's expensive to build the turbine, the pump, the tunnels, excavate, and have locations where this is appropriate, close to the demand. So of course, there is drawbacks and advantages in technology. This is a maturity graph which shows the capital requirement to develop the technology times the technology risk. And this curve works more or less like this. I had an idea, and this idea is amazing idea. It's a great idea. I'm gonna make a lot of money, but have a lot of risks. But the amount of money that I have to put is very, very small in order to, for example, get a patent the idea. This research and development. So this is kind of is the risk that I'm taking that maybe one day this technology is going to be accepted and it's actually going to work and become an innovation and people will use in the future, combined with the very small cost that you're putting into this solution. So it's kind of like if you want to develop a technology, you look at this graph and you see, okay, which are the technologies which are very new but still need a lot of investment and have high or low risk. Then the idea is that you invest, you pursue the technology, you work with it, and it reaches a point which is somewhere around here that the risks starts to reduce, and the amount of the chances that you have that you will actually become a viable solution in the future might increase, might not, but the risk reduces. But maybe you need actually to put a lot of investment in this industry to make it competitive with others, and it's not a good idea. You might as well stay with the other ones. So these ones are the ones that the risk is high, but the investment is low. These ones are the ones that the risk is low, but I might as well use the ones that already exist. But the risk of failure is low. The only thing is that you have to put a lot of money. You guys understand more or less? This curve exists for almost every niche of technology. For example, within batteries, they have this energy storage. You talk about desalination. You talk about different type of services, transport. They have this curve, and people use it if they're a company innovative company that wants to see where they want to invest. This is very useful graph. So pump storage is the most mature. You have peak storage, which is the one that I showed about Denmark. cold water storage. This is the one that I mentioned about the aquifers, which already exists, and then you have several other ones. Thermal. These are thermal energy storage. These are electricity energy storage solutions.
Professor,
Yeah.
don't we have gravity storage without water?
Sorry?
Gravity storage,
Yes.
but without water then.
Yes, there is a lot of people working on this and developing the technology. Given that you ask, I can give more details in a future lecture. I have already written a paper about about the subject, and there's a lot of people interested on this. There are several different alternatives and possibilities and technologies which are being considered. Some of them will pass this curve, some of them will reach this, and maybe one of them will reach this curve in the future. But this is the thing. If it makes sense to use hydropower, pump storage, hydropower, and it's an option, then the other technology will probably not reach maturity because it will always make sense to
Sure.
to build the other one. Yes, but it exists. There are several alternatives. Yeah, I'm not going to go through all in detail because we're going to talk to them through the course. Right? Yeah.
Julia,
Uh-huh.
could you talk about flow batteries? I don't know how.
Yeah, flow batteries. They have two tanks, separate tanks, and they are liquid. They I'm not 100% sure how they work. I will add in the lecture, of course, on batteries. I'm gonna have to do several battery lectures because most people are interested in batteries. I'm gonna show the feedback from the students. And at the moment, I have a brief idea of how it is, but I'll prefer to go through in more detail and in a future lecture. Is that okay?
Okay, thank you.
Thank you. Yeah, and so another approach to look into technology innovation, to see, compare different technologies, to see how they compete with each other for energy storage. You have this graph where you have project price in kilowatt hour capacity. So this is the capacity. So this is the discharge and charge capability. It's not the storage itself. It's to store, to charge and discharge the storage. And here you have the cumulative installed nominal capacity, which is also charging and discharging. The price here is the existing capacity. And then you see that lithium ion batteries are lowering really quickly. You have electrolysis in the past, which also is cheap. The problem with hydrogen is also you have to store, you have to compress, you have to transport, you have to then transform into electricity with fuel cells. So these are the fuel cells, which is coming down really quickly also. So this is up to 2015, so not very old. In 2011, this one compares with pump storage. This is pump storage. Not 2011, sorry, 2020, today. If you want to think of building a pump storage facility, it might make more sense to build a lithium ion battery. But I'm not sure here is 2011. This graph is a little bit not 100% correct. I was looking for a better one, but I couldn't find. But it's interesting to compare how these technologies vary. And of course, the main driver for the slope of this curve, so as quickly as it comes down, it means that as much people invest on it and put money in order for the technology to become cheaper and competitive, and it requires a lot of money, for people to do this. People are mainly interested in lithium because of the EV sector, but given that the cost is coming down, it can also be used for home energy storage or any storage in the grid, just because it kind of took the boat with the EV. Lithium is the lightest solid material on Earth, which can be used for battery. That's the reason why lithium is so interesting for cars, because it just becomes a light battery that you can drive with. So other energy storage technology which were not mentioned in the previous graphs are the mountain energy gravity storage, which is similar to a pump storage site, but with salts or granites that you can use. There are several other ones where you can use gravity to store. This is, for example, swimming pool thermal energy storage, which the idea is to turn a swimming pool into a ice tank for storing cold heat from the winter and use it during the summer. And in the winter, you can use the heat as a heat sink for a heat pump. So then you can enhance your energy efficiency for heating up your house in the winter. And then once you produce a lot of ice, you can use the ice for cooling down your house. There are several alternatives for graphene ultracapacitors, graphene batteries, and there's a lot of research into this. And it could be even competitive with chemical batteries in the future. Also, liquid air. There is a company which is investing a lot of money. Some investors have a lot of put a lot of money into this, which could be a competitive technology in the future. I'm going to talk in future lectures about these other technologies. Am I going too quick, or is that okay? I'm not sure. Well, if you have a question, please stop and ask. So far we have a list of technologies that people prefer, subjects, reference themes to be discussed in this lecture. And the first one is batteries. I found it funny because we are in a mechanical engineering degree, and batteries are kind of chemical engineering, more related subject, because it's all chemistry and membranes and cathode anode. There's no moving part, but it's great. Let's do it. So I'm going to spend a lot of time learning about batteries to teach you guys, because I don't have so much knowledge now, but I will. Don't worry about it. Smart grids, yes. Thermal energy storage, transport, long-term energy planning, computer modeling, energy storage economics, applied focus, grid energy storage, hydropower, energy storage regulation, hydrogen, pump storage, off-grid energy storage, demand-side management, hourly energy prices in Brazil, biomass, biogas, fossil fuels, innovation and patent, theoretical focus, cryogenic energy storage, other mechanical energy storage, compressed air storage, and ultracapacitors. Yeah, so ultracapacitors is definitely more of a electrical engineering course. I'm happy that you guys are so interested. So yes, I'm going to base my lectures in the future focus on this, on your opinion. And today I'm going to talk about hydropower. What is hydropower? Why hydropower? First, because 70% of the energy in Brazil is generated by hydropower. Hydropower is the most well-known energy storage technology. And yeah, my research has been focused on hydropower, pump storage mainly. I have worked in several other energy storage technologies, but this is the main focus of my research. So the people most interested is Conrado, Lara, Patrick, and Eliezer. So I would like to, before I start the lecture, ask what is your interest on hydropower? Why hydropower, Conrado? Oh, you want to start?
Let me see. At first, I think I need a little bit of a background about the subject. just to know the landscape and some theoretical principles maybe. But I believe I would like I would like to know about the sites, the existing sites in this technology.
Perfect. Lara, what's your interest in hydropower? Just for me to focus the lecture on it.
Okay, then. I think it's an interesting subject, and we have a lot of potential in Brazil, so I want to learn more, to be more situated in the scenario and what do we have around the world and so on.
Perfect. Patrick?
Yes, I worked in a company doing projects for hydropower projects.
What's the name of the company?
VEG.
VEG. Very nice. Small hydropower. Small.
Yes.
Okay. Micro or PCH?
PCH.
Awesome. Very interesting to learn from you then. Eliezer?
Eu vou falar em português.
Of course.
Certo, no meu país, é claro, eu sou estrangeiro aqui, eu acho que existe muito potencial de aplicação da PCHs como uma fonte que poderia ser em complemento, porque até no momento meu país ainda usa muito termoelétrica, então seria interessante a aplicação desta.
Qual país você vem?
Eu sou de um país lá da África, Guiné-Bissau.
Guiné-Bissau?
Exato, não sei se já ouviu falar.
Sim, já ouvi falar assim. Guiné-Bissau, ela fica em volta do Gabão, né?
Não muito longe.
Guiné-Bissau não tem muita montanha, né? Muito flat. O potencial de usina de hidrelétrica é muito pequeno lá, mas dá para fazer pequeno, né? PCH.
Exato.
Beleza. Obrigado, pessoal. Thank you so much, guys, for your feedback. Let's start the lecture then. Hydropower. So starting with the theoretical parts to get it out of the way, it's very, 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 very similar compared to other technologies or other energy storage technologies, the technology aspect of itself. You have three main equations. One is hydropower generation, which is hydropower generation joules per second, watts. Not joules, watts. It's joules per second. And it's equal to the height of the difference in height that you have from the top of your reservoir to the bottom of your reservoir. You have the flow of water that goes through the turbine in kilograms per second. You multiply the acceleration of gravity, 9.81 meters per second squared. And then you multiply an efficiency factor, which is usually 90% for a hydropower plant. Literally, that's as simple as it gets. And using this equation, you can have a very good idea of how much your hydropower solution will generate. Of course, the turbines, the head and the flow will vary the turbine that you use. There are several different turbines for high head, for low flow, high flow, and then you choose different turbines in order to optimize the efficiency from your system. Energy storage, which is the topic of this lecture, is literally the average head, so the average difference in altitude between the upper reservoir and the lower reservoir, times the amount of water that you have stored in the reservoir, which varies, of course. You have a section that varies in kilograms, and you multiply by the acceleration of gravity and by the efficiency of the system. And the value is in energy, joules, is not in watts. But I made this presentation and this is from here. Yeah. I'm sorry. The only difference is that instead of F here, which is the flow of water, is S, which is how much water you have available to generate energy. So how much energy you have stored in your reservoir. And then the next one is this average head is because while you're using the water that you have stored, the head difference reduces because you're consuming water, the amount of water in the reservoir reduces, and then the heads that you have to generate energy also reduce. The higher the heads, the more energy you generate with the same amount of flow. The lower the heads, the more flow you need to pass through the turbine to generate the same amount of energy. But for energy storage, you can get an average of this head. And then you have the energy balance, the mass balance, which is the inflow, the amount of water that comes into the reservoir with the river flow, with precipitation. So the amount of water stored, the water storage is equal to the amount of water that comes in, less what comes out from through the turbines, the flow through the turbines, what comes out through the spillage. I put V because it's usually vertedor in Portuguese, but in English it's spillage, minus the evaporation. So then this is also very important equation. So this is mainly the background, theoretical background, basic theoretical background. I'm going to go through more details about other aspects. For example, the type of hydropower plants based on head. So there are power plants with low head. They're usually more expensive because you need a larger turbine that allows more flow to go through. They will generate less energy per meter cubic per second of water that flows through the turbine. They're usually not a good alternative for storage because the head is so small. If you reduce the reservoir a little bit, it has a large impact on the head, which impacts the amount of energy that you generate in this plant significantly. In Brazil, we have very few ones. For example, in the Paranapanema River between São Paulo and Paraná, we have the Pimental Dam, which is before the Curva do Xingu in the Belo Monte Dam. We have Santo Antônio Geral, Bom Retiro is in the Taquara River, Santo Antônio Geral and Madeira River. Most of the hydropower plants in Brazil are this one, medium head. We still have a significantly huge potential for low head, which we don't even consider because we still have some potential for medium head, which is cheaper and more convenient than low head. Medium head, you have this reservoir which can vary something like 20, 30, 40% of the head of the total head, and this is used for energy, water storage, energy storage in Brazil. In Europe, sometimes these dams are only store water for a day, for a week storage, because the impacts that they have in the river is high if you go down the reservoirs a lot, and they're very concerned about the environment, so they focus these type of dams in run-of-the-river dams. In Brazil, it's different. Another one is high head dams, which you have. So this is from 5 meters to 20, medium from 20 to 150 to 200 meters. This one is 200 meters over. They're usually connected with a pipeline, so they don't have a dam. They have, of course, they have a dam. They have a small dam, but the connection with the upper reservoir with the lower reservoir, the discharge river, is connected with a tunnel. They are connected with tunnels, similar to pump storage, but they sometimes don't store energy, they just generate hydropower. In Brazil, we have Passo Fundo in Uruguay River. There is a city called Passo Fundo. When it rains in Passo Fundo, this water goes into the reservoir called Passo Fundo. There is Cubatão, which is close to Santos, which is in the Serra do Mar, between connecting the coast with the plateau where São Paulo city stays. And they have a head of 750 meters. Nilo Peçanha is similar to Cubatão. Is a system that the lights used transpose water from the Paraíba do Sul River to supply water to Rio de Janeiro. And in this process, they also generate some electricity. Capivara is in the Capivari River, which is close to Curitiba. They have 730 meters dam also, a huge head. So these three are are very old dams. They are not used as much as they used to be because you're kind of wasting water that would go through a huge basin. You're cutting a corner and generating power in taking water from the basin on the top to throw directly to the ocean. So you're kind of wasting water, but you have a big head to generate electricity during peak hours. So they usually just generate electricity during peak hours. Ponte Nova is a new one in Mato Grosso. It's in the Correntes River, which is in the Paraguay Basin.
Professor?
Yeah.
Like you said, the shape of the lake, it's important to storage the water. In here now we have Itaipu. I don't know the term in English, but it's hydropower by fio d'água.
Yeah.
We don't have the storage in the lake. So we have Itaipu with a great potential to generate energy, but it's not the excellent place to storage water in that case. Is that right?
Yes, exactly. I was going to mention this because it's a very awkward and weird and difficult to explain project. This is the project you're saying is exactly right. So they have a huge amount of water they can store. This here, which used to be the Seven Falls, which is Sete Quedas, which used to be something similar to the Iguaçu Falls, but 10 times larger. And they decided to flood all this area. What they could have done, they could have built the Itaipu Dam in here or somewhere around here. The problem with here is that they wouldn't have space enough to stack all the turbines because they take a lot of volume. Even in the Itaipu Dam, they have to kind of do different sections because there are too many turbines. The vertedouro has to fit, so they put it here, they chuck it there. So they needed space, but they didn't need to flood all this. There was no need to have such a huge reservoir, and they would not lose generation capacity if they build one reservoir here with 10 times lower flooded area, and then a smaller reservoir here because it would provide the same service, which is run of the river generation. It doesn't have storage capacity, but. Yeah, so the reason why they built Itaipu 1 maybe is because of the space, but if it was because of the space, they could have built here or here, different locations, which they would also have physical space. And the other one is just that you wouldn't need to build two dams, and building two might have been a little bit more expensive. But the thing is that back in the day, the cost to the environment had no impact. So if it was 10% cheaper, okay, flood this huge area. It makes no sense. But now that we have this reservoir, if, for example, in 50 years, we need more reservoir storage capacity, we can use this as a storage reservoir. The only problem is that the dams upstream, they already regulate the flow, and the flow that reaches the Itaipu Dam is already kind of flat, and it can be used to generate.
Yes.
So the idea is that if you reduce the head, you would reduce the amount of energy that you can generate per megawatt per second, meter cubic per second per flow. So if you lower the head of the Itaipu, you would generate less energy with the water that comes in. So it's a debatable subject, and in the end of the lecture, I'm going to explain why this project was definitely not good for Brazil, and it's a completely different reason. Thanks for asking. It's a run-of-the-river dam. It has a huge storage, but it doesn't use the storage because it's better to maintain a larger head to optimize hydropower. Do you guys understand? More or less?
Actually, I'm a little confused. I never understood actually this case of Taipu because we have this huge reservoir of water, but it works a fio d'água.
Yes.
For me, it's not clear yet how we have it in Itaipu.
Yeah, people say that the reason why is that they wanted to have a huge reservoir in case they go into war with Argentina. They can blow up and flood Buenos Aires, and I think it's not such a good idea. But maybe that's the reason. I don't know.
Okay, so we don't have a clear reason for this huge reservoir, right?
Maybe they want to spend a lot of money.
Yeah, so we have to spend the money. That was the time to do that.
Yeah. Okay, we need to spend money. Let's get a huge project to spend a lot of money getting debt and be 40 years in debt. Maybe that's why. I personally don't know really the reason. It's a very good question because one of those things is not run of the river. It's not storage. It's a combination. It can be both, but
it was not the greatest years for Brazil.
Yeah, it wasn't. People weren't really thinking about hydropower dams. They were more thinking about something else, which I'm not sure. Right, so talk about run-of-the-river dams. Yeah, so run-of-the-river dams, the reservoir doesn't vary. It's always the same. And why is that? Because you don't want to cause impact in the environment. So if you lower this reservoir, you create an area between the reservoir and the surrounding of the reservoir, which will have environmental impact, social impact, and it's not very nice thing to do. So what you can do, you can build a small head hydropower plant, or you can generate a dam here on the top of the river. If you have a waterfall or something, you construct a channel or a tunnel in order to go a little bit forward instead of flooding the cascade or this drop. You just create a tunnel that reaches this point, and this point you have the head, and then you generate hydropower. This is used in Brazil mainly in the south of Brazil, in the Antas River. So Antas River in the Rio Grande do Sul, people are more concerned about the environment. They have several of these where they build the dam here. The river goes around, and then the height here reduces 20, 30 meters, and then they build a tunnel. So this is a tunnel, and then the power station is here. So in the south of Brazil, Antas River, different locations in the Rio Grande do Sul, they have this run-of-the-river dam. And another interesting aspect is that you can build water locks to combine hydropower generation with waterway transportation, and it's convenient to have the level of the reservoir fixed because it reduces costs in dredging, in maintenance of your waterway if you maintain the level fixed. And it's great because Waterway transportation is one of the most energy efficient, maybe the most energy efficient inland transportation solution, depending on, of course, the project or what you want to transport. Storage reservoirs. Storage reservoirs is just literally you have a reservoir which varies in height, and you design this in locations where you have a valley topography which allows you to have this variation. This is in Austria, Kaplum, for example, in the winter, when the electricity prices are higher, they use the water that they store in the summer when the ice in the mountains melts, and then in the summer the price of electricity is lower. They store energy to generate during the winter. In Brazil, is during the wet period, when it rains a lot, the reservoir fills up in order to use during the dry season to regulate the flow of the river. There are different hydropower reservoirs. There are good hydropower reservoirs, literally, and bad hydropower reservoirs. The good ones are the ones which have a topography which is in a valley, which they have a high level variation with a low, very small section of degraded land, which is resulted after you using the reservoir. There are very bad reservoirs where you have very small reservoir variations and result in huge areas of degraded land. So the good reservoirs, they need very few land. They don't need so much land because you have, in the amount of land that you have, the reservoir can vary a lot. So if you have 50 meters level variation and comparing to a 5 meters level variation, you would need a 10 times larger reservoir for the 5 meters level variation. The 5 meters level variation, you have 10 times more evaporation also, because you have that huge reservoir, sun, wind evaporating the water. It's more expensive, and also the impacts are higher to the environment and to the society. So always focus on these type of reservoirs. So in Brazil, we have the highest reservoir is Serra da Mesa, which is this type of reservoir. But the problem is that is up in the Tocantins River basin, and it has never been filled up because the catchment area, the area where the rain flows into the reservoir, is small, huge reservoir, 42 gigawatts médio. This means that if it's filled up, Serra da Mesa, if it's completely filled, and you generate energy, you can generate 1 gigawatt for 42 months. Let's say 3 years. So for 3 years, you can guarantee 1 gigawatt generation, not only in the Serra da Mesa, but in the Serra da Mesa and the dams that comes below, right? Furnas, 30 to 35, then Sobradinho, Nova Ponte, Emborcação, Três Marias, Itumbiara, Tucuruí, Serra da Mesa, Ilha Solteira, Bento Munhoz, que também é Foz do Areia, Marimbondo. These are the largest reservoirs in Brazil, talking about energy. So the higher they are, the higher the altitude, the more number of dams that you have below them to generate hydropower, the higher the number. The higher energy area is Sobradinho in the São Francisco River, right in the border of Bahia and Pernambuco. 4.1 kilometers squared is something like 10% of the area of Rio de Janeiro state. Huge, massive. You have Tucuruí, 3,000 kilometers squared. Balbina is also massive in the middle of the Amazon, close to Manaus.
Professor,
Serra da Mesa, yeah.
with the highest area, we have also high evaporation.
Yeah.
Right. So it's not the perfect place to storage.
Yes, because particularly the region where Sobradinho is very dry. Is the driest place in Brazil. Is the Cerrado in the middle of Bahia state. Yes, it's not great. It's in average the amount of water that comes in, something like 10% evaporates, depending on the year. The reservoir is if the reservoir is full, if the humidity of the air. But it's one of those things that the water would flow straight to the ocean. So evaporating water there, it kind of reduces the temperature of the region. The water circulates back to Brazil because the wind always pushes inwards, because you have the ventos alisios. So it's kind of a geoengineering project, which
Yes, we changed the microclimate.
yeah. Exactly. So comparing the size of the reservoir, the area of the reservoir, you have Nova Ponte, which is in the Paranaíba Basin, which is the one that has the most effective reservoir that requires less land to store energy. Then Embarcação, Bento Munhoz in the Iguaçu River, Barra Grande is in Uruguay, Serra do Facão, this is in Iguaçu also, Caconde. So these are good ones. But then you look at the bad ones, which should never, ever should be considered. Well, I'm going to talk about why. They store something like 200 times less. So Curuaúna stores 200 times less than Nova Ponte. Balbina stores 150 times less than Nova Ponte. They're really, really, really bad reservoirs. So, for example, Sobradinho is one of the bad ones. Tucuruí, also one of the bad ones. And I'm going to talk about that. So these are mostly in the Amazon region. That's very flat. So that's why it doesn't make much sense to build reservoir storage in the Amazon forest. The other reason is because, for example, Sobradinho reservoir is the size, 10% of the size of Rio. And when it dries, what happens is that 50% of the area vanishes, disappears. So this is the workable altitude, because it doesn't go all the way. The minimum altitude is never reached because it just doesn't make so much sense to lower the. So this is the height that usually changes, 50%. And then what you have is that if there is Remanso, there is a city called Remanso here. When the reservoir lowers, you have to walk literally 50 kilometers to reach the reservoir, because you have a 50 kilometers area where is degraded land. This is, for example, Remanso is here. So you're looking at Remanso, and this point here is this mountain. So it's something like 70 kilometers distance. Is a long way, is a huge area where it's not used. In this area is Cerrado, so I mean there's not so much things going on, but if you do this in the Amazon region, you have in the middle of the forest, you have a new reservoir, which they didn't bother even to remove the trees. They just flooded the reservoir. It's completely absurd what they did. But anyway, when the reservoir comes down and you use the reservoir, all the forests that existed around this area, they had to kind of adapt the biosystem and everything, because from one day to another, the river was there. Now the river is 20 kilometers. After 6 months, the river is 20 kilometers. 20
And
kilometers.
it's also,
Huh?
it's also important to say that when you have trees that go under the water, we have the production of methane.
Yeah.
And then we have another problem with climate change. So the clean energy becomes dirty.
Very dirty, yeah, exactly. Much more dirty than coal, probably. And yeah, but to be fair, nowadays this Tucuruí region is all grass anyway, because they managed the deforestation of the Amazon reach here. But this could happen in Tapajós, and it's a huge impact in the environment, huge impact in the society, right? If you have a plantation and the river just becomes 50 kilometers away. People want to swim in the river, to jump and have fun, to sail, right? And then the river goes down. It just have a huge impact on the area. The area is just unused. No one, the value goes down. You can use for agriculture. Agriculture you can use for nothing. So these are bad reservoirs, yeah? So bad reservoirs should not be built. And maybe it should be decommissioned, and good reservoirs should be built. So there's this issue with reservoirs, which lately there is a lot of discussion about reservoirs. And yes, we have to agree, it's not good for Brazil, it's not good for the economy, it stores energy, but there are several other alternatives that you can use. In the next lectures, I'm going to talk about some alternatives for these type of reservoirs. Yeah, so I already talked about Itaipu, the Itaipu concept. And then now it's why we need to store energy, why it's so important to have these large reservoirs. The main reason is because the southeast, the amount of water available for hydropower generation varies significantly. So in the wet period, when there's more rain, January, February, March, there's a lot of water. And then in the dry period, there's not so much water. The idea is to store this water and use it during the dry period so that you have a constant amount of flow to run the turbine as optimum as possible, to generate electricity during peak hours if it doesn't rain, to have water to use the hydropower plants as best as possible and lower the cost of energy. The same happens in the northeast, the same happens in the north region. North region, the difference between the wet period and the dry period is even higher. And in the north, you really should not build hydropower storage reservoirs. Right. So how does the storage reservoirs combine with run-of-the-river plants? You would usually build these storage reservoirs on the top of your basin to regulate the flow for the rest of the hydropower plant in your river. For example, this is the Iguaçu River. The rain that happens in this part of the basin will flow into the Foz do Areia dam, and you will store this dam is the biggest dam in the south of Brazil, Foz do Areia, and then you store all the rain that happens mainly during October, November, September, which are the wettest months in the basin, and then you regulate the flow and you guarantee that you have always water to generate energy. The other thing is that when it rains a lot, and if you didn't have storage, what happens is that all the water will just flow through the dams, will not generate electricity. So that's why it's important to have storage reservoirs on the head of the river, and it's important to have run-of-the-river dams below in order to maintain the head. As I said, higher the head, the more electricity generation you have per meter cubic per second of water. So this is kind of the representation of a basin, of a hydropower basin. Here is the Cataratas do Iguaçu. And these are the reservoirs in Brazil, the spread, the distribution of reservoirs in Brazil. You have Serra da Mesa, which is the largest here. You have Tucuruí, which is the one that I mentioned that has a huge impact. Nowadays, not so much because there is no environment there anymore. It's all deforested. You have the main part in Brazil where you have storage reservoirs at these sections, which is the head of the Grande River, Paranaíba River, Tocantins River, and São Francisco River. Sobradinho is also a huge reservoir, which is here, has a huge impact also. And it stores a lot of water that precipitates in this section of São Francisco and here there is something like 300, 350 meters of generation head of dams generating electricity. In the south of Brazil, you have Foz do Areia and the Iguaçu River. You have Barra Grande, Machadinho, and Campos Novos. Oh, you have Passo Real here. Here is Passo Real, and here is Passo Fundo. And here is Antas River. Antas River has no storage reservoir, only run of the river, which is a huge disadvantage because it only generates when it rains there. They probably should have built a storage reservoir. So these are all the main major storage reservoirs in Brazil. Today, so this was yesterday. Yesterday we can see the level of storage in the reservoirs. The southeast region, which has 70%, was 21% capacity of storage. The south region, 22, which is the record low, is the second lowest. The lowest was in the beginning of the year, which was terrible. The south of Brazil stores 6.9%. So if you wanna know how much each energy storage reservoir stores for Brazil, you can look at here also. I'm not gonna go through all of them. You can have a look. I'll send you the presentation. Northeast, 18% of the storage, mainly Sobradinho. You have Três Marias also, which is a large reservoir. In the Amazon, you have Balbina, Tucuruí. Serra da Mesa is in the southeast, but the water they store in Serra da Mesa here also contributes to the northern generation, which is Tucuruí, the main dam in the north. I mean, now the main dam in the north is Belo Monte, but Belo Monte doesn't count as north. Oh, no, it does. Belo Monte counts as north. I'm sorry. There are some dams that doesn't count as north, which is in the Madeira River and the Telespires River, the Sinop Colíder Tapajós. I'm not sure if it's going to count as north or southeast, but there are some dams which are in the north which count as southeast. You have to be careful when you run the comp, the same wave, and you want to know the price of ELD, where each hydropower plant counts for each region. This is taken very seriously in the formulation of the price of electricity for Brazil. Hydropower generation has been the main electricity source in Brazil. And 2013, 2012, 2013, 14, it reduced significantly. It never went back again. During 2012, 13, 14, what guaranteed the supply of energy in Brazil was the thermoelectric power plants with gas. Thank God we had a lot of wind power being increased. It also helped to avoid having to ration energy as it happened in 2001. Last year you had less wind power generation because in the beginning of the year it rained a lot in the San Francisco Basin in the northeast. And when it rains a lot in the northeast, the wind power reduces significantly. It rained a lot in the beginning of the year and it's raining a lot now because of La Nina. La Nina event pushes the humidity to the north section. So it rains a lot in the Tocantins River. It rains a lot in San Francisco River. It rains more in the Paranaíba, in Três Marias, but it rains lower than average in Tietê, Grande, Paranapanema, Iguaçu, Uruguay, and the Jacuí and Antas rivers. So we are in the strong La Nina. It's not strong La Nina, it is average La Nina, but given that the temperature of the world has already risen 1 degree Celsius average, given that the temperature of the Pacific is 1 degree lower, it should actually be 2 degrees lower because the temperature of the whole world increased in 1 degree. So it is a strong La Nina. It's supposed to be a low, but it is strong. And the impacts are very, very clear of a La Nina year this year we have in Pacific. Be very careful with the storage reservoirs in the south, which is not the case. It's not happening. ONS is not really helping the south to supply its energy requirements. I'm not sure why, but they are doing a very bad job guaranteeing the supply of energy in the south. Hydropower vulnerability is one of the issues of Brazil. We had several crises due to lack of rain, due to droughts. We had in 1924, drought in São Paulo, which caused a crisis. 1938, 50, 63, 67, 83, 87, 95, 2001, 2014, and we're still in crisis today. I wrote a paper for Renewable Sustainable Energy Reviews that was like 4 years ago that I suggested that there is a cycle of crisis which follows a 10-year pattern, which goes like this, as you can see, goes crisis, no crisis, crisis, no crisis, crisis, no crisis, crisis, no crisis. There was not a crisis in 1971 because there were several dams which were constructed this year. Furnas, Três Marias, Ilha Solteira, several dams were built this year, so they had excess capacity, they had excess hydropower, excess electricity. They started distributing electric showers for people to take showers with electric showers because they had so much electricity. And in this paper, I had the conclusion that the reason why was a circular energy or climate cycle for 10 years. Every 10 years, you have 5 years that rains a lot, 6 to 8 years that rains a lot, 3, 4 years that rains less, and so on. But in the end of this lecture, I'm going to present another paper, which I published this year with Natalia, and gives another reason, which I personally think is the main reason why this energy crisis happens in Brazil. So this is a postdoctoral, this is a graduate course, masters and PhDs. The idea is that I'm not teaching you guys. This is kind of a debate. That's why I always want to hear you, because we're doing research here, right? Nothing is set in stone when you're doing a master or PhD. This is the energy storage in the Brazilian reservoirs. This is the maximum energy storage capacity for all the dams, and this is the demand. So when we were in 2001, 2002, we had a crisis, and then we had the rationing of energy, and the energy demand reduced it something like 20%, and then it took something like 5 years for it to go back to what it was, mainly because of energy efficiency measures to reduce consumption and stuff. Economy, of course, the energy rationing had a huge impact in the economy of Brazil also, so it took a long time for it to go back to normal. Economy go up, and now COVID. So COVID crisis also something like 20%, 15 to 20% impact on electricity demand. But this is the demand. We're talking about storage. What happened is that in 2012, 11, so the end of 2011, 2012, we had a reasonable amount of water in the reservoirs. Our previous president, female president, decided to set a law which had the intention of lowering the costs of electricity for everyone, which is great. Yeah, let's have cheap electricity. But the problem is that it relied a lot on the fact that it would rain, and it had rained in the previous years. So then what you did, you use all the reservoirs, and the reservoirs reach here. But then what happens is that the reservoirs never went back to what they used to do. The reservoirs never filled up again. And I'm gonna explain, give a reason why in the next, as it goes, the lecture. So the other issue is that the storage capacity stopped increasing, but the demand keeps increasing, and then the amount of energy storage that we have per demand is reducing. In the past, in 2001, if all the reservoirs were full, we could supply the demand for 6 months. Now in 2021, if all the reservoirs were full, we could only provide 3.3 months of electricity. So this times 3.3 is equal to this. Here, 2001 times 6 is equal to this. And another aspect which reservoirs have, so when the reservoirs are low, as I mentioned before, the amount of heads that you have to generate the same amount of electricity reduces. So you need, for example, for Bento Munhoz, the highest head is 135. The minimum head is 93. Now we are operating at 3% capacity at Bento Munhoz, Foz do Areia today. So the head is something around 94, 95% meters. So we would need something like 30% more water, that we waste a lot of water to generate the same amount of energy if the reservoir was full. So we're in a situation that we are not in a good situation, right? We need to waste more water to generate the same amount of energy. So this is the reservoir, full reservoirs and low reservoirs, and it's good to have this storage capacity in order to, if it rains, then you don't waste the water. But of course, there is a balance between being full and having a higher power, requiring less water to generate the same amount of energy. If they're compared, if you have the reservoirs at a lower altitude. This is for San Francisco. This is when the reservoirs are full. Nowadays it's raining. Last year and this year is raining a lot in San Francisco, so the reservoirs are relatively high. Três Marias varies 46%. Sobradinho varies 44%. The main generation capacity in the São Francisco River is this section, Xingó, Paulo Afonso, and Itaparica, Mochotó. There is also some proposals for two low head dams in this section to make use of this change in altitude for hydropower. But I haven't really heard much about actually building this. This section is too flat. The low reservoir will result in a large flooded area, and all the water will evaporate, and you won't store and you won't generate. So this section makes no much sense at all to build power plants in here. Maybe this section here. There is Formentera. There is a dam here being in the planning stage. Might not ever be built, but this is a section which is interesting to build a dam. So now we're going to talk about daily energy storage. So we talked about seasonal energy storage, about daily energy storage. Daily energy storage is also one of very, very important reasons why countries invest in hydropower. For example, this is Austria. Austria has run-of-the-river plants. And in Austria, run-of-the-river plants are run-of-the-river plants. There is not even 1 centimeter variation, maybe 1 centimeter, because you can see some variability here, but very, very little variability in a hydropower generation during the day. So here is how much run-of-the-river generation you have, and here is the storage reservoirs, which are not big storage reservoirs, but 1 day, 1 week storage reservoirs, which are these ones. And they vary a lot. So, for example, during the winter, you have a variation of power generation in these plants up to almost 100% for the storage reservoirs, but for hydropower itself, you have something like 54% variation for overall hydropower. In the winter, this increases to 72%. So, this is great for the energy market, because they can guarantee the peak supply for electricity with hydropower, which is very cheap. Base load electricity is much cheaper than peak load, and hydropower provides peak load. So Brazil does a similar thing. For example, in the southeast, you have total variations with run-of-the-river and storage reservoirs, variation of 37% in the summer, where the demand is higher, 48% in the winter. The summer is a little bit smaller because you have run-of-the-river dams in the north now, which generates at full capacity because they don't have storage, and the flow of the river reaches maximum and they start spilling. So that's why the variability in the summer is lower. In the winter, the dams in the north reduces. So this is very important for Brazil. Brazil should start focusing on using this hydropower potential for peak generation instead of base loads. So, which I'm not sure why they haven't really going in this direction. This would be very convenient for Brazil. This is the south of Brazil. South of Brazil uses even more than the southeast, because it's not really a base load type. It is base load. It shouldn't be base load. It should only be used for peak generation, the south, in order to save water. For this not to happen, what happened in the beginning of the year, what happens is that there was no more water. All the water was gone. All the reservoirs were empty. So you have 40 gigawatts, which is something like similar to the capacity of Itaipu, which you could have for generation, peak generation, which is very expensive, which if you want to do this with a thermal power plant, it would cost something like 500, 600 reals per megawatt hour peak generation plant. And you don't have, why? Because you don't have water, because you use all the water. So my proposal for Brazil would be to make sure and manage better the water resources that we have, use these plants like this, guarantee that you always have water to generate during peak times. You don't use these reservoirs, this water for base load generation. You guarantee that even in 2 years that you generate for peak generation, you still have water there. So this is not to happen. So this is happening now. Brazil is importing 2.4 gigawatts of electricity from Uruguay and Argentina. Argentina is buying coal from Indonesia to supply the electricity demand for the south of Brazil. So now if you turn on the electricity in your house, parts of this electricity is being generated from coal shipped from Indonesia. As incredible as it sounds.
That's so efficient.
Extremely efficient, yeah, exactly.
To have all the logistics to import, it's amazing.
Yeah, we are paying them a lot of money for them to do this, because if they didn't, then we might actually eventually have to ration or turn the coal power plants in Rio Grande do Sul, which are even more expensive than buying coal from Indonesia. And I'm not sure other reasons. Probably cheaper to do that than to turn on the thermal power plants in the south of Brazil. Or maybe what they're doing, they're trying to dilute the costs, not to. So if you descolar the PLD, what happens is that the people from the south will have to pay much higher than people from other regions. But that doesn't matter now, because we are already in the teto of PLD. So this week, the CMO, which is the cost marginal custo marginal de operação, it's already 730 reals per megawatt hour. So today would make no difference because we already paying the highest price for electricity in the whole of Brazil. But yeah, maybe that's a policy to try to make the life.
And also the environmental impact of the burning coal. That's not here. Will come maybe with the rain, but
yeah. So maybe we're more concerned about our air quality than the air quality from people in Argentina.
yeah,
Exactly.
we must remember that Brazil was sued by Uruguay, if I remember right, caused the acid rain in the past because the burning coal here in Rio Grande do Sul.
Wow. No, I didn't know about this. So the coal from Rio Grande do Sul has a lot of
Sulfuric.
Sulfate. Thanks for sharing that. Okay, following the same rationale, we have that, for example, in the end of 2014, we have the reservoir of Paranaíba, which is in São Paulo, but supplies the water from Rio de Janeiro, was used for hydropower generation, but it reached the point that we didn't have water to drink because we wasted water for hydropower generation. It's incredible, right? So, well, if somebody with a little bit of common sense, is planning and operating these dams, they would always try to maintain the level of the reservoir. This is a pluriannual and reservoir, right? In 3 years, you see the level of the reservoir comes down, particularly because if you have 3 or 4 years of drought, you still have water to supply water, right? Not electricity. And then that's why you reached a point that you had no more water, and Rio de Janeiro had to ration water. There was a lot of counties there, municipalities which had a water shortage, and the water quality reduces because you didn't have enough water to dilute the sewage that people throw into the rivers. So there was a huge problem there, crisis. Thank God it doesn't happen again. The level today there is something like 23%. I really like hydropower, so I follow almost every day like the level of the dams in Brazil, and I it was one of my hobbies. Anyway, another topic which I mentioned and people were interested is PLD. PLD is the name of the cost of electricity in Brazil, and the impact of hydropower is almost is around 60%. 15% is the demand. For example, if it's a very hot day and everyone's turning on the air conditioning, maybe next week the price will go up because of the running the same. They change the demand and the impact of PLD. You have the reservoir having impact of around 15% also. Storage reservoirs. So if the storage reservoirs are very full or very empty, it only impacts 15%, which in my opinion shouldn't be this way. It should be the opposite. So the reservoirs should impact not 60, but at least 40%. That's one of the reasons why the energy sector is so vulnerable, because they don't take it seriously, the storage, but it is very important. And the other aspects nowadays, you have wind power, you have hydropower plants which are not delivered in time, you have transmission lines which are not delivered in time, so kind of management issues and wind power. And now I have this curve, which is cause versus consequence curve, and I would like to ask you, which curve is impacting the other curve? Is that the blue line is impacting the orange line, or is the blue line impacting the orange line, or the orange line is impacting the blue line? If you, analyze and check, what would you say? Cause and consequence. Anyone?
Show me the R squared.
Yeah, that's If you could teach me how to do that, that would be great. I don't know this methodology. But looking at it, what do you say? For example, you have this line is low, and then this line reduces, and then this line increases, and then this line follows it, right? And then the blue line reduces, and then the orange one starts to reduce also, and then the blue line increase, and then orange line stops reducing, or is that the opposite way around? Well,
I don't. For me, it's not clear which is changing first.
yeah, exactly.
It's look like a mixed behavior. Sometimes it's orange, sometimes it's blue.
Mm-hmm. Yeah, perfect. So showing these curves means is that storage is the orange, so storage varies, and then the blue is the ENA. ENA is the amount of water that you have available to generate hydropower. The energia natural afluente. ENA is like the amount of water that you have that could be generating electricity without taking into account the storage. So ENA also takes into account that some of it can spill, can be wasted, some of it is stored, some of it is not stored. Maybe you have ENA very low, but you have a lot of storage, so you can generate hydropower. ENA, energia natural fluente, means that is the water in the river that could, assuming that you have no dams, no extraction of water, is how much electricity you generate at that moment, given the flow of water that's flowing through. If you had dam that can generate energy with all the water that passes through the hydropower plant, it's very cool, very complicated aspect. But if you want more details, I can give more detail in the future, probably because I have 15 minutes. Yeah, so what I'm trying to say here is that, of course, this ENA, which is the flow of the river, will impact the amount of storage in the reservoir. So if you have a storage reservoir empty and you have a lot of flow, the flow will fill up and increase this storage reservoir. But my paper that I'm going to talk about now, which is the last thing, argues that the storage reservoirs, the level of storage reservoir in Brazil impact how much rain is going to happen in Brazil. If the storage reservoirs are low, it will rain not much. The rain pattern in Brazil will lower because of the impacts of the reservoirs in the climate. And I'm going to give a little bit more details on that. So Natalia is part of this research. And the argument is that the reservoirs in Brazil are so large that they have substantial impact on the weather. São Paulo, for example, 3.5% of the area of São Paulo are reservoirs, 1.6 of Paraná, 1.5 of Minas, and 1.7 of Goiás. And the reservoirs in Brazil, they have a huge variation in area and variation in head. For example, the Billings has 99%, can go completely empty. Furnas is 63 of the area that varies. That's not the heads, that's the area, the flooded area. When it's full and when it's empty, it varies 63%, 64, 65 for Três Marias. Barra Bonita, Jurimirim is a small variation. Passo Real in Rio Grande do Sul, 81, huge also variation. So generally, they vary a lot, the area. And the proposal, the justification, the argument that I'm trying to make, that I made in this paper, and it was accepted by Climate Exchange, which has impact factor of 5, so it's a respected donor, is that when the reservoirs are full, what happens is that the basin, it gets encharcada, it gets wet. So the whole basin above a montante of of the reservoir, it gets wet also. So the soil gets wet, and when it's wet, what happens that it evaporates more water, which reduces the temperature of the region, increases the average, the relative humidity of the region, increasing the relative humidity of the region and reducing the temperature. If you have a warm or cold front reaching this region, what happens that the chances for raining increases. On the other hand, when the reservoirs are low, what happens is that there is less humidity on the ground, there's less evaporation on the basin. Having less evaporation on the basin, the temperature is higher, the relative humidity is higher. When you have a warm, humid front coming from the Amazon or a cold front coming from the south, it just passes. It doesn't rain.
This is the phenomenon of the flying rivers.
The phenomenon of the flying rivers, exactly. The warm and humid front is the flying rivers, but the flying rivers, they just go straight to the Atlantic Ocean. It rains in the Atlantic Ocean because it's too hot, it's too dry in Brazil to rain. So I created a methodology to prove this, and for example, Itaipu, the flow of Itaipu before the construction of the dams were something like 30% lower than today. The dams in the south also increased significantly the flow of the dams in the south, but it had an impact on the dams in the southeast. The dams in the southeast have a different, so the amount of storage in the dams in the southeast dictate how much it rains in the southeast. So if you compare these values of ENA, the values for energy storage, they meet similarly to them. Unfortunately, I only have data for storage until 2000. I don't have data for storage until 1930, so I couldn't compare with this data this correlation, but I'll compare in the next slide. But the idea is that as many hydropower power plants that are built close to Itaipu or in the Paraná Basin, the higher is the flow of Itaipu because it rains more. But if you build for example, one dam in Itaipu, a huge dam in Itaipu, the amount of precipitation increases in Itaipu, but reduces from other locations also. So there's also this aspect. And this is the impact of the rain, the reservoirs. So for example, here is where Emborcação, where in Tumbiara, where the storage reservoirs are, this location. So I'm analyzing the amount of precipitation here and the amount of precipitation in Iguaçu, Itaipu. And when the reservoirs at the southeast region, these regions are high, which is this yellow line, what happens is that the amount of precipitation in Emborcação here increases. So they follow the same line. Okay, this is a bit obvious. Of course, if it rains more there, the reservoirs increase. But at the same time, the amount of rain in Itaipu reduces. So when it rains more in Emborcação, the rain in Itaipu reduces because given that you have a larger flooded area here, the wet and dry water that comes from the Amazon hits this location, which is cold and wet, the chances of precipitation is higher. It rains here, and then when it reaches Itaipu, it doesn't rain anymore because all the potential for rain is already exhausted. So that's kind of the justification of the paper. And going back to Itaipu Dam, so if people in the past had built Itaipu with a lower flooded area, what would happen is that it would reduce the amount of rain in this location, and it would allow, for example, cold fronts coming from the south not to exhaust all its cooling potential for creation of rain, and this this cold front would reach the southeast and produce more hydropower. So the construction of Itaipu, I even have here construction of Itaipu in the year when they built Itaipu, they made sure all the reservoirs were full enough, were very high full. So they planned, the whole Brazil planned to have the reservoirs of the southeast as full as possible in order to reduce the time for Itaipu to fill up. But it happens that given the reason that the reservoirs were full, it just rained a lot. And it rained like it has never rained, because during the dry period, in the beginning of the wet period, the reservoirs were very full, and Itaipu Dam filled up in 1 year just because the reservoirs were completely full. Yeah, I could talk about this a lot longer, but we'd like to hear your thoughts on this. And before I conclude the paper, so we talked about the diversification of energy storage types and how that could be an alternative for energy storage. We talked about the methodology for energy storage, which can be applied for different technologies. We talked about technologies for energy storage. We showed the preference for each student on energy storage. We introduced hydropower. We talked about details on hydropower in Brazil, talked about the benefits of hydropower for peak generation and also for daily storage, and also the impact of hydropower reservoirs on the climate. Thanks, guys. Do you have any questions, any suggestions, any opinions, interests? I had to talk really quickly because there was a lot of content. I don't want to go through more than one lecture about hydropower. There was a lot to talk about hydropower in Brazil.
So many things to process. A lot of yeah.
Julian, can you hear me?
Yeah.
Julian, congratulations, a very nice paper. Congratulations to you and Natalia. I have one question about Dilma in 2016. I didn't understand what she expected to do, actually. She wanted to reduce the cost by decreasing the reservoirs in order to, what she expected to happen, actually.
Yeah, so what happened is that it's the CPME 428, something like that, which had the intent of reducing the cost of electricity and lowering the I don't know exactly what was the regulation details. Probably Flavio would know much better than I. Explain exactly what was the law, but the law had to, companies had to join this proposal of kind of having a certain amount of money that they would receive, and the government would then operate the electricity sector with their own, with their, as they thought they would receive a fixed amount of money, which was not very good for the energy companies because they couldn't, for example, play with PLD, with the changes in PLD and stuff like this. Only Eletrobras joined, but Eletrobras is like 30% of the electricity generation of Brazil. Maybe back in the day was even more, like 40%. And the intention for her to do this is to reduce speculation and to reduce the cost of electricity. But ONS decided not to dispatch thermoelectric power plants in order to guarantee that they wouldn't have to pay the amount of money that they were promising with this regulation. And it's incredible. in my paper, I explain what was the consequence to the electricity sector. But basically, what happens that in Furnas Dam, they started to spill a lot of water. So here, this reservoir capacity, they spill a lot of water from the top of the Blendy River. They were not generating electricity with the spilled water for 2 or 3 dams. They just go straight away to increase the generation in the dams in the downstream, because they didn't want to turn thermoelectric power plants during peak hours. But they wasted a lot of hydropower potential. So that's why you have this huge drop. So this happened in Embarcação Dam, this happened in Furnas Dam, this happened in Nova Ponte, Três Marias, all the dams in the top, which were filled, large, full of water, and she threw away. But the problem is that she was expecting that it would rain the same as it rained before, but it didn't, and it haven't rained since. It literally destroyed the energy sector, unfortunately.
Unfortunately, it became more expensive actually, our electricity.
Yeah. But she had good intentions, and probably well, let's give she wasn't expecting that she would. So the energy crisis had a huge impact on her popularity, and it was just a stupid idea. But no one published this. No one showed the impact of reservoirs the reservoirs had in the amount of rain. So she didn't know this. I am quite sure that people that were managing the energy sector in 2001, that the reservoir levels reached very, very low. They were very used to this dynamic of having full reservoirs raining more and having impacts on the climate, and they were thinking more, and they lived this, the construction of the dams. They saw the impacts of the dams in the climate, so they knew that this happened, and then they realized that if they didn't do energy rationing, what would happen is that the reservoirs would never fill up again, because the rain was not going to fill up the reservoirs again, because it would stop raining. They were very happy because in 2-3 years the reservoirs went back to normal. Maybe what happens that the people, they forgot. New managers arrived there. The ones that had this idea, they knew how the energy sector operated, died. That's all speculation, of course.
All right, thank you.
I get really excited with hydropower. Anyway, any other question?
That's good for us. We have a lot to learn with you.
Thanks, Natalia. Okay, so next week, we'll have pump storage to complement this hydropower. I'll try to finish everything I have to talk about pump storage. I published like 5-6 papers about pump storage. There's also a lot of knowledge about pump storage. Pump storage is the main energy storage technology today, but of course, might not be in 10 years' time. Probably batteries are going to take over pump storage. But yeah, so I saw that pump storage is very low in the interest list. So I'll try to wrap up everything in one, maximum 2 lectures, and then start the other topics which are more of interest to you. And please, for the people that did not sign the confidential agreement and send your interest things, please send it to me. And so today there's no homework. This is still the same homework. And if you guys like one of these ideas which I'm talking about, and you want to write your projects about these ideas, these proposals, anything that I talk here, please feel free. And if you want to talk to me and ask questions about the project, also I'm available. Okay, guys, I think it's enough. See you next week.
Thank you. Yeah.
Thank you.
Thank you, Julian.
Bye.
Thank you, Julian.
Have a nice week. Bye bye.
Bye.
Thank you, Julian. Bye bye.
Bye, Julian.